Local search algorithms are discussed in different artificial intelligence books. In Russell and Norvig, they are discussed in chapter 4. Here we're going to take a look at the basics of local search algorithms, starting with hill climbing search, simulated annealing search, genetic algorithms, and finally local search in continuous spaces. Now, before we look at the local search algorithm, let's try to understand what kind of problem does it solve. The kind of problem that this search algorithm solves is an optimization problem. In an optimization problem, how we get to the solution is not that important. What is important is the solution in itself. So the goal state is the solution. So when we talk about the state space, it's a set of complete configurations. And we have to find the optimal configuration. So if we were to look at a problem such as the TSP or the traveling salesman problem, we have to find the optimal configuration of solution. Another problem that we can think of is a timetable. So we've got a set of classes, we've got a set of different instructors, and then we've got subjects. Subjects have time constraints, students have time constraints. So all of them together come up with a problem, and we have this timetable that we need to resolve. So we have to create a timetable which solves all the constraints in a satisfying manner. So a mechanism that we can use in this case is the iterative improvement mechanism. So we take a current state and then gradually try to improve it. So since this is constant space, it can work on algorithms which are online as well as offline. So let's look at the traveling salesman problem. So we start with the complete tour. Here we take the tour and gradually change the different pairs. So this is one pair, this is another one, and then there's another one. So the way this works is we add an additional connection over here and also over here. This approach is very nice because you can literally get to the optimal solution even with thousands of cities, and this approach gets to you to very close to the solution, such as within 1% of the solution. So once you get to the 1%, you can do little manipulations and get to the actual solution. Another example is an ant queen problem. What is an ant queen problem? In the game of chess, we have a board. The board has white and dark places, and then we've got a number of different pieces. And for now, we are only concerned with the most powerful piece of all, which is called the queen. Now, the queen can attack horizontally, vertically, and diagonally, any number of places, as long as it's not blocked by any other piece. So the goal of an n queen problem is you have n queens which we have to place on an n by n board. So the idea is that there should be no conflict. So no two queens at any given time should be on the same row, column or diagonal. So let's start with our configuration. So we've got 4 queens. In this case, we've got several attacking pairs. So this is one, this is another one, here, here, and here. So a total of 5 conflicts. Over here, if we change one of them, so just this one, if we move it above, you see the conflicts are resolved. So now we just have 2 conflicts. And if we further move this one down, we've got 0 conflicts. So, and this is a good solution. So it almost solves instantaneously, the problems of finding a solution. So we've got queens, we've got boards, and then this looks very easy because it's a 4 by 4 board. But what if there's 16 by 16 board with the 16 queens for the solution and so on? So the number of possibilities are endless in this case. So let's look at the basic hill climbing algorithm. It's also called the gradient ascent or descent algorithms. Now, why is it called the gradient ascent or descent? Because as you will see, sometimes the solution is at the top and at other time it is at the bottom. So it's either like climbing something like the Everest, where there's thick fog, so we cannot see more than what's around us, and with amnesia in the sense that we don't really remember where we are, where we want to go, and so on. It's also like going deep into the Mariana Trench, which is the lowest point on Earth to our knowledge, and so if you put the average inside the Mariana Trench, it will go and it will be submerged. So in the basic hill climbing function, we've got an input which is the problem, and the return is a state that is a local maximum. What is the meaning of a local maximum? We'll see in a minute. So the inputs are a problem, and then we've got some local variables to keep the state. One is the current node, and then there's a neighbor node. It starts by making a node of the initial state of the problem. So the initial state is converted from the problem into a current state. Next we have a loop. It's a simple loop. In this loop, we start with the neighbor and then we give the highest possible value of successor of the current. So we take something called the objective function and find out what is the best possible successor of the current. If the value of the neighbor is less than equal to the current one, then you return the current one. Otherwise, you make the neighbor the current. So this is a very simple algorithm called the gradient ascent or descent or hill climbing algorithm. If we look at the same algorithm using a graph, on the x-axis there's something called the state space, and if you notice here, this is a one-dimensional space, but imagine that this is 3, 4 or even 10 or 15 or nth dimensional space. So you take in all these inputs and then you get a point, and this point is what's called the objective function. So this one. Now we have to understand some topics here. The first is shoulder. So the way it works is we start with any point. So let's suppose we start with this point and we try to go up. If we want to go up, you know what will happen? When we get to this point, we'll be stuck for some time at least, and this is called the shoulder. So on the other hand, we start over here. We'll actually reach the best possible solution, which is the global maximum, which is actually the optimal solution. On the other hand, if we were starting from here, what will happen is we'll reach a place and we'll think this is the best, but this is essentially not the best. This is called a local maximum. We can also get stuck on flat local maxima, such as this one. Now, how do you avoid this? You can avoid this by doing a random restart. So you start and look for a solution, and when you cannot move ahead, you restart from another totally random location and try to find out if your solution is better than the last one. So this is called random restart hill climbing search. Another solution could be through a random sideways move. So when you're stuck, you basically want to move sometimes randomly. The good thing is it will be able to escape here and eventually get to this point and go up. However, it will be stuck in a loop if you are on local maxima.